You are back with Mike Yegerbo and John Beeler. Let's talk artificial intelligence and how it can be used to hopefully battle the COVID-19 virus. On the line, we've got our good friend Sasha Luccioni. She is the Director of Scientific Projects, Artificial Intelligence for Humanity at Mila. Thanks for joining us, Sasha.
I'm glad to be here.
So artificial intelligence is used for a number of different things, but you guys are researching on how you can battle the COVID-19 virus. What are you guys up to?
So when this all started, we reached out to some colleagues of ours who work with the WHO and the UN, and what started out as a conversation ended up as an article. So we wrote an article about how AI can help fighting the COVID pandemic, and we identified a bunch of different ways. Essentially, scientists, we want to know all the different options before we settle on one. So we figured out that, we can work on vaccine creation, we can work on improving CT scan identification, on epidemiology, on all different scales. And so essentially we published this paper, and people at Mila, so there's a bunch of researchers working on different parts that we identified. So there's a group of researchers working on, for example, using AI in order to explore all the billions of possible molecules that can eventually be treatments for COVID. So essentially they do this by simulating the molecular structure of the COVID protein and the molecular structures of the other molecules that they're looking at, and seeing how they bind together. And based on this, it's basically a simulation in AI space. And based on this, you can predict what their affinity is, and the better they bind, the more chances there are of using them as a treatment, essentially. So there's a group working on that. It's really interesting because you can essentially search, hundreds of millions of molecules in a relatively short amount of time, which can take a lot longer if you're synthesizing them and trying them in vitro. So AI can help kind of create this simulated world for vaccines and for cures, which is, they're making some really great progress. It's pretty exciting. And then there's also some researchers working on, for example, how to optimize ventilator attribution in hospitals based on projections. So essentially using different levels of data, so national data, regional data, municipal data, in order to predict, for example, tomorrow how many patients there are, and so to allocate resources within a hospital and within a public hospital system in the way that for example, sometimes they can even send ventilators from one region to another, from one county to another, knowing that there's going to be more patients in that county. So that's a really interesting project because they're using real data and kind of making predictions in real time. So that's really exciting. And then we have also a researcher working on improving diagnosis of COVID using CT imagery. So he made actually this website where you can download his model and test it on CT scans, so they can use this in hospitals. And it could actually be a good way of testing for COVID while waiting, for example, for a positive diagnosis. So for example, someone arrives in a hospital and they have symptoms, and then they send out their test, but during the 24 hours that it can take sometimes to get a positive diagnosis for COVID, you can use CT scans to kind of get an idea of whether, what the probability of that person having COVID or not is, and then something that can be coupled with the eventual tests. So it's another thing that's been being worked on.
Well, talking about, I think a lot of people are concerned about a vaccine right now. You talked about how artificial intelligence is being used to see virtually how, you said a billion different molecules would bind with the COVID-19 virus. Has this been done before with artificial intelligence? How effective has it been if it has?
So it hasn't been done for a vaccine. It has been done for antibiotics. So essentially, I don't know if you know, but we're having more and more drug-resistant bacteria, and so there have been cases. Essentially, the issue is that there's such a large space that can be explored, even for antibiotics. There's different types of antibiotics, and some of them are more large scale or narrow. And so essentially, using AI, you can explore spaces that haven't been explored before, and then essentially create molecules that we haven't, either that don't exist or we haven't discovered yet. So for the antibiotics, it has been used, and there was a publication, I think it was just last year, as a proof of concept, but it's never been used for vaccines yet. So this is a completely brave new world.
No, it's fascinating. For the antibiotics, how much did that speed up the process? Do you have an idea of that?
Well, so essentially the bottleneck is testing. So once you identify some molecules, after that you can synthesize them and you can test them in vitro using samples of the virus, essentially. And then you can already get an idea if it's working as well in your petri dish as it worked in your simulation. So that's like a first step. And then say from like 100 promising molecules, you'll narrow it down to 20. But then those 20 still have to be tested in mice and humans and et cetera, et cetera. And so the bottleneck is always going to be human testing, which is good because you want it to be safe, and there are things that should be explored, right? So I think with AI, it can give you kind of an idea of things to test, but it's, for example, it can't predict how humans will react to the vaccine because it doesn't have that data. All it has is the data of binding, right? There's no anatomical data as such, physiological data, so they don't know. Maybe the molecule that it proposed is actually poisonous to humans. That's something that has to be tested down the line, you know.
Yeah. But it's
sorry, Mike. I was going to say, it basically helps you speed up the process of elimination, at least to narrow your focus and figure out where to spend the actual lab time instead of trying to go through every single thing, like the billions of molecules, like you mentioned, right? So
exactly. And then typically, for example, for antibiotics research, it's been kind of a hit or miss, or you know that this family of molecules, there's a lot of antibiotics in that general direction, so you'll go there. Well, what if there's this whole other family of molecules that you haven't even looked at yet because it just hasn't come up yet, right? So actually, like antibiotics have been discovered by accident in a lot of cases, right? And vaccines, it's taken years and years of work to discover this, and you still base yourself off of, you know, other things, like things that have been working for different types of flu, right? Like you can base yourself off of something, but you'll always, you know, be biased in that direction. And AI can kind of helps you open the perspectives a bit larger and say, well, this molecule, maybe it's used in something completely like different. Maybe it's like, you know, something that's organic. Maybe it's a compound that's found in onions or some random thing. And then maybe it will help, right? So it's like, yeah, it's a way of broadening your horizon.
You know, my question is, this is all fascinating, and I can see how this would speed up, you know, the research. But you talked about the testing, not having the human physiological data. Will we get to a point in the future where we'll have that digitized so that we could test these things virtually on virtual humans? You know what I mean?
I think that I know that personalized medicine is becoming more and more of a thing, but I think that even if you sequence someone's genome and you really know exactly, you know, what we're made out of on a cellular level, there's also other levels that are harder to predict. For example, you know, an organ level or an environmental level or et cetera, like things that we're being exposed to and side effects of our condition changing. For example, what happens like if you sequence someone's genome, but then they become diabetic or they have high cholesterol, that's something that I don't think we're at the point of detecting that on a molecular level yet. So I think that there's work to be done in terms of understanding how we work better, because AI is all about data, and the better the data is, the better your simulation is going to be. So I don't think that we're there in terms of creating, you know, a virtual human, like how the brain works. If we want to cure Alzheimer's with a drug, right? We don't know how the brain works well enough in order to input that into an AI algorithm and tell it, you know, optimize whatever this is. We don't have an idea, a clear enough idea.
How far away do you think we are from that? Is that like years, hundreds of years?
No, I think it's probably in the next 20 years, we'll have some breakthrough. I think that the brain is kind of the last frontier because it's so complex, but for things that are a bit more simple, I don't know, like blood pressure or something, you know, things that are a bit more straightforward, we can make progress faster. But a lot of people are actually working on the connection between, you know, neuroscience and AI, because they realize that it's kind of an anecdote, but neural networks, right? Neural networks are a tool of AI, a type of algorithm that is inspired by the brain. But we're so far gone now in terms of neural network architectures that no one talks about it being brain inspired anymore. It's kind of like, yeah, well, back in the day, someone came up with it and it was inspired by the brain. But there's this whole kind of 180 that's happening. And then now that we're talking about bio-inspired AI and vice versa, like neuroscience using some discoveries from AI. So there's like a lot of connections being made now. And I think that the more that these kinds of connections are made between neuroscientists and AI practitioners or clinicians and AI practitioners, the more we have a potential of finding something that works in both cases.
We're talking with our good friend, Sasha Luccioni. She is an expert researcher into artificial intelligence at Mila. We're going to have to take a break. When we come back, we'll chat with her a little bit more about some of the computing power that is necessary to make this happen. Back after this. Do you mind if we just keep you on for another few minutes here?
Yeah, fine. Am I clear enough? You can tell me if I use long words or something.
No, surprisingly, you're actually really good. I'm understanding everything, which is fantastic.
Okay.
A lot of times when we have nerdy people on, they kind of get into the weeds, so to speak. I tried
it when I feel myself going too far off. I tried to.
No, you're fantastic. You're fantastic. Okay, let's. John, are you ready?
Yep.
Okay. Here we go. You are back with Mike Agerbo and John Beeler here on Get Connected. So we're talking all about artificial intelligence and how some researchers are using it to attack the COVID-19 virus, everything from developing vaccines to diagnosis of folks that have it. On the line, we've got Sasha Luccioni. She's the Director of Scientific Projects, Artificial Intelligence for Humanity at Mila. Sasha, what kind of computing power do you need to make this happen? We talked about scientists using artificial intelligence to basically research how well like 1 billion different types of molecules would actually bind with the COVID-19 virus. Is this something I can go down to Best Buy and buy an HP laptop and start doing this, or are we talking big computing power?
The approach that's being used in the molecule discovery project is called reinforcement learning. And the way that works is that essentially you have, it's the same approach that was used for AlphaGo, all those kind of game-based and Atari and things like that. So essentially you have something that you want to complete a task, for example, discovering a molecule that has 100% binding power with COVID. And essentially you're trying to optimize the way that you do this task, and you do it hundreds of thousands of times. So essentially it doesn't require that much computing power as such, because the approach used, the neural network, is not that complex, isn't that deep, but you have to do it a lot of times. So essentially you can do it on an HP laptop. It'll just take you a while because you have to you can run it one by one task by one task, but you can also parallelize it. And then essentially in order to make several threads, several parallel experiments, for that you need GPUs. So that is beginning to be a kind of a mainstream thing. And the more efficient your GPU, the more powerful your GPU, the more parallel tasks you can have going. So at Mila, we do have like clusters of GPUs, but it's not actually, that's the thing. It's not a question of, having this really, really powerful computer. It's essentially a question of finding the perfect way to tune your task so that it gets completed successfully. So then you have to play around with parameters and things like that. So that's where it gets messy. But in terms of computing power, it's really not that bad.
So you talked about GPUs, and just for the listeners, that's a graphical processor, right? Like yes. in a video card, for example.
Exactly, yes. So it exists nowadays, and most computers, a lot of computers have them, especially gaming computers. Now what's used a lot for machine learning are TPUs, which are tensor processing units, which are like the next step from GPUs that can have like a lot of more parallel computations per second. Essentially, why a GPU is better than a CPU or more efficient in any case for machine learning is that you can have more things going on at once. You can have more parallel computations at once. That doesn't mean it can store more memory, have more storage. It just means that it can do parallel things. It can multitask better.
How's that compared to like our brains? Can we parallel task? I know as a man, I have a hard time doing more than one thing at a time.
I wasn't going to go there. No, but it's interesting. So Joshua Benchio, who's our scientific director of Mila, he's working a lot on neuro-inspired AI. And so essentially, as humans, we tend to have two ways of processing things. We have the fast route and the slow route. And so, for example, if you're doing something like you're doing your dishes, it's going to tend to take the fast route because you've already done this before, I assume. So you have things that you do on more or less autopilot, like driving, like walking, right? You don't really think about putting one foot in front of the other. And then you have the slow kind of processing thing. That's when you have to learn a new task or learn about GPUs. Then your brain can kind of slow down a bit and you have to go slower. And so right now, the way that AI works, it's mostly kind of this automatic, fast processing, like you don't really think about what we're doing and you just put data in and you just get stuff out. Essentially, the AI that exists now is more of this fast processing speed, like you have a robot washing dishes. But we haven't figured out how to do the slow, kind of rational, logical thing. We can't ask a neural network to explain why a decision was made, why a certain molecule binds with another. That's still kind of up in the air. And so he's concentrating a lot on this kind of explainable AI, on the slow AI part, but this is a whole new domain of AI.
So slow AI. You think you'd want fast AI, but slow AI is where it's at in the future.
Well, we have computers that can do like really fast facial recognition, but then again, when we ask it, why, like for example, if something goes wrong, right? If someone gets misidentified using a facial recognition algorithm, the machine won't be able to tell you why this person looks like someone on FBI's most wanted list. They're not going to be able to say, well, they have a similar nose or this guy has a baseball hat or whatever. And so this is where a lot of people are working right now. Explainable AI, transparent AI, ethical AI. That's like a really important part of AI right now, because we realize that fast is good in some cases, but even if your autonomous car can drive, you still want to understand how it's making its choices.
Why did you knock John off the side of the road on his bicycle?
Right. And then what if there's bias, right? What if all of a sudden you realize that it's discriminating against a certain, race or gender or something? Like all of these things are really unclear in AI algorithms right now.
We're talking with our good friend, Sasha Luccioni. She is the Director of Scientific Projects for Artificial Intelligence for Humanity at Mila. Thanks so much for joining us today.
My pleasure.